And so the here to here is also A. 2A is equal to D. So the only difference is that A is half of D. Okay? So this is known as the dipole moment of a pair of charges. What are its units? It's meter times coulomb. So meter coulomb. That's the units of dipole moment. Now, when we get to magnetism in chapter 30, I believe 30, I'm going to define for you the magnetic dipole moment. No. The magnetic dipole moment mu is going to be the current of a current carrying loop of wire times its surface area. So the same thing exists in magnetism as exists in electricity, the concept of the dipole moment. Then the torque experienced by a dipole moment is equal to its dipole moment cross product with the electric field. So the torque is what makes it rotate. You see? In other words, if the P and the E are lined up together, what happens? Is there a torque? No. Which is another way of saying if the P is this way and the E is this way, that's it. It's happy. It doesn't want to turn. You see? How about if the P is this way and the E is to the right? What's the torque? It's 0 also. But it doesn't want to be there. So if the P is this way and the electric field is this way, there's no torque. It's kind of like this. Please, please move me. Please, please move me. If I give it a little kick, that's it. It's going. You see? So it doesn't have torque on it, but it is waiting there. It's an unstable equilibrium. Okay? And let's see, what are the units of this? Now, what is the units of torque from Physics 1? What are the units of torque from Physics 1? Newton meter. Okay? So what was the units of the dipole moment? Meter coulomb. What are the units of electric field? Newton per coulomb. Therefore, the units of this work out to be what? Meter Newton. Okay? So therefore, the formula makes sense. Again, anytime you have an equation or a formula, try to see if it makes sense. The units work out, and if it makes sense in the limiting cases. You see? Okay, the next equation is the potential energy equation. Minus P dotted into E. So this is the potential energy of the dipole inside of that electric field. Now remember, at the beginning of the lecture I started out by saying electric field has a energy density in it. But this is not the same thing as that. This is the potential energy of the dipole that it has inside of that electric field. Okay? So let's see if it has, again, let's see if it has units of joules. It's got to have units of joules. This is, P is meter coulomb. Electric field is Newton per coulomb. Well, again, it's what? Coulomb, coulomb cancel, Newton meter. And a Newton meter is a joule. Well, here, Newton meter is a torque. Now, why in one case Newton meter is a joule, the other case Newton meter is a torque? How do I know which is which? Here's the answer. When you take the dot product between two vectors, what do you get? Scalar. Energy is a scalar. So the one that's a scalar is the energy. If you take the cross product, you get a vector. Okay? So, okay, now what are the limiting cases here? P and E. What is the potential energy of this system? Their angle between them is 0, so their dot product is minus PE. So that's the most negative the potential energy can be. What do systems like to do to their potential energy? Always like to go down, right? So when they're lined up, that's the most negative, which is perfect, okay? When they're anti-lined up, what's the potential energy? Take the dot product between the two. Cosine of 180 is -1, so you get plus PE, which means that's the maximum potential energy. So when the electric field is this way and the dipole moment is that way, it's maximum. It doesn't like to be there, but it just needs a little kick. Oh. Ah, there it is. It turns. You see? Potential energy goes to lower potential energy. Okay, I want to do